Hello, everybody. Welcome to this week's colloquium. So today we are very happy to have Ollie Burke with us. So Ollie is nearing the end of his PhD at the Max Planck Institute for Gravitational Physics in Potsdam, Germany. He's worked on a number of projects which have to do with data analysis and the science for the space-based interferometer LISA. And today he's going to tell us about constraining the spin parameter of near extremal black holes using LISA. So Ollie, you can now take it over.
Magic. Okay, fantastic. Just a quick question. You guys can see my slide and my cursor, yeah?
Yes.
Okay, excellent. Thank you. So first of all, I'd just like to say thank you so much for the wonderful introduction. It's so nice to be able to be here to talk about some of the work that I've been essentially smashing my head off a wall trying to understand for the past year and a half. Now, the beauty of this is that this whole project is a very simple question. If we were able to observe gravitational waves coming from a small object falling into a very big black hole, where the black hole is near extremal, how well can we measure the spin parameter of the primary black hole? So I think it's important to kind of start this off with a bit of a story about how this project came about. And I was starting my PhD, trying to learn about some data analysis and extreme mass ratio in spirals in general. And I read an amazing paper called In Spiral into Gargantua, which the authors Sam Gralla, Scott Hughes, and Niels Warburton are authors of. And they were basically looking at gravitational waves being emitted from near extreme black holes where you have small body going into it. Now, what's amazing about these waveforms is that they have a very unique characteristic. They have a very flat profile, and then they exponentially begin to decay as this point called the innermost stable circular orbit is approached. And the question we had was that in this dampening feature, which is unique to these near extremal sources, how much information is there in the spin parameter? So John tells me, go away, do some calculations, and I go away and I approach him very excited saying, wow, John, look, we can constrain the spin parameter to 1 part in a billion. And John takes one look at me, and he's the smartest guy I've ever met in my life, let's be honest here. And he takes one look at me and he says, you must have done something wrong. That doesn't make any sense. Go away and repeat your calculations. So I go away and I repeat my calculations, get back to my desk, run some codes, and I come back with the same thing. So he's like, this is interesting, okay. And he gives me 5 different checks to go to make sure I hadn't mucked up any of my calculations. I come back and all of those checks pass. So we're both looking at this numerical result, and we both desperately want to think, why? Why does this happen? What is so special about this dampening feature here that allows you to constrain the spin parameters of these sources to roughly 4 or 5 orders magnitude greater than it would be for moderately spinning sources? Okay, so hopefully by the end of today, you guys will leave thinking, right, if there are near extreme black holes out there and we observe these gravitational waves, we will be able to constrain those spin parameters to excellent precision. And that's the purpose of today. So let me go through the roadmap. This is what I'm going to tell you. Okay, so the first thing, I'm going to give a very quick review on the gravitational wave detector LISA, some emeries, and also just general stuff about some near extreme black holes. And then I'm going to offer you some analytical results on how well we expect to constrain this spin parameter, right? And this will motivate the numerical sections that happen afterwards, where we use fully relativistic waveforms to figure out how well we can measure this parameter. So that's the numerical results. And then finally, we discuss some conclusions, some future work that we're thinking about, and then we can have a nice friendly discussion about the things that I've spoken about today. So first of all, this is a nice movie that I've just shamelessly copied off Wikipedia. I apologize, but I do think that it does show LISA very well. So LISA, the Laser Interferometer Space Antenna, is a gravitational wave detector that will be sent into space in 2034 and will be able to observe gravitational waves that typically lie in the millihertz regime. So such sources could be massive black holes. So this could be the collision of a few million solar masses smashing into each other. And other such sources will be things like extreme mass ratio in spirals. And that consists of a small body falling into a very, very large black hole. Now, one point I want to make is that LISA is not LIGO. LIGO is L-based interferometer, ground-based, and we'll be able to detect gravitational waves typically in sort of 10 hertz to a kilohertz regime. And the signals that they were to observe will be very short. They can lie between milliseconds to a couple of seconds, if you say a binary neutron star. LISA will be able to observe gravitational waves that elapse over, say, 4 months to the entire LISA mission lifetime. This is a data analyst, like me, worst nightmare. It's very difficult to model these sources, and in particular, it's immensely difficult to computationally expensive in particular, to actually perform parameter estimation on these sources. So let's talk a little bit about MRIs, which is pretty much the focus of my PhD. So here are some beautiful animations that a very close friend of mine, Lorenzo, developed. So like I said before, an MRI is the in-spiral of a small compact object falling into a massive black hole. And the in-spiral itself will decay due to gravitational wave emission, which is dissipating energy away from the system. Now, as you can see on the bottom left, these orbits are very complicated. They're typically eccentric, inclined, and the way that these MRI waveforms are typically developed is using a field called black hole perturbation theory, where you assume that instead of having the two-body problem, you have a central primary Kerr black hole, and that Kerr black hole space-time is being perturbed by an external object, and you measure those perturbations traveling off towards infinity. Okay, so the setup that we're going to consider is we're going to have a very small compact object with secondary mass mu, and is going to be in-spiraling on a circular and equatorial orbit around a massive black hole. And the mass of this massive black hole is very large, such that the mass ratio itself is very, very small. Now, I'm pretty sure it was Chandrasekhar, so apologies for the pronunciation if I screwed that up, was the one that basically said that black holes are the astrophysical black holes, so we're going to be ignoring charge for the time being, are the most perfect macroscopic objects within the universe. That is, a Kerr black hole can be described by two parameters and two parameters only, its mass and its spin. We will be considering masses, which are roughly 10 to the 6 solar masses, but we're going to be considering spin parameters that are very, very close to 1. So spin, because we're dealing with prograde orbits, we're typically going to have the spin between 0 and 1. It's 0 if it's a Schwarzschild black hole. It's 1 if it's maximally extremal Kerr. We're going to be looking at the spin when it approaches 1. And in particular, we're going to be evolving these in-spirals all the way up to the innermost stable circular orbit, which is the minimum radial coordinate at which point stable and circular orbit applies. And in particular, what you'll see about these near extreme black holes is that you get unique qualitative features very, very close to that ISCO. So I'm just going to talk a little bit more about these near extreme black holes. So like I said, the spin parameter approaches 1, but an interesting feature about these is that in a particular set of coordinates, Boyer-Lindquist coordinates, the innermost stable circular orbit approaches the horizon of the black hole. Now, that what is amazing about about these sources is that there are many complicated expressions in just general Kerr black holes, which can be massively simplified, because introducing this new parameter, which I'm going to call the extremality parameter, defined as so, the square root of 1 minus a squared, when you take this guy in the limit as epsilon approaches 0, you have complicated expressions such as the ISCO, let's say, and you get very, very simple representations. But what's important to take away from this is that the Boyer-Lindquist radial distance from the ISCO and the horizon typically scales with the spin parameter itself, right? Now, the picture I have here is from the film Interstellar. Most of us have probably seen this. The black hole in that, which they call Gargantua, typically has a mass of around 10 to the 8 solar masses, but it's a near extreme black hole. It has a spin parameter of roughly 1 minus 10 to the negative 14. And the question is that if Gargantua was out there, will LISA be able to find it? Okay. So I'm just going to get straight to the point, okay, of our results. So what we were able to do, we were able to build fully relativistic waveforms for 2 different viewing profiles. We did this from scratch. So we have 2 sources. So we're looking face on to the source. So if you imagine this is my black hole and we're spinning round, we're looking down on it. That is for face on sources. And for edge on, we're looking at the orbit as it's going round. And you get 2 very different sorts of profiles. So you get a nice kind of flat profile like you see here, but you get this exponential decay in the amplitude of the signal, okay? The reason this just looks like a great big blob is because there's so many tiny oscillations here. Okay, this is a waveform. I have a zoom in on this later on in the actual talk. Okay, and the question is, how well can we constrain the spin if we observe this dampening regime? Well, our calculations suggest if you look down to the bottom left here, that throughout the dampening regime, you were able to constrain the spin parameter to 1 part in roughly 10 to the 10. And what's important is that you need to observe this dampening feature in order to be able to constrain the spin to such high precision. If you notice up to the dampening, I'm only getting 1 part in 10 to the 7. So it's very important you see that, it's very important that you see the waves emitted when you're really within the near horizon geometry of that near extreme black hole. Now, this wasn't enough for us. We want to see, all right, let's try and take this as extreme as we can. So we took spin parameters from 1 minus 10 to the negative 4, so 0.49s, all the way to 0.99s. And you can see you get this exponential increase in the spin parameters precision, which is amazing. Okay, so the point here is that if it's near extreme and we see the waves, we can constrain the spin parameter to excellent precision. But let's try and answer why this is the case. But before I do this, I think it's very important for me to motivate why you guys should actually care about any of the stuff that I'm talking about. Well, number one, this is a perfect sort of opportunity for us to be able to use results that were developed by people in the high energy physics community that work with the very detailed mathematics behind near extreme curved black holes to link them to actual gravitational wave observations. And in fact, if it wasn't for the group at Harvard developing a lot of the various formalisms behind near extreme Kerr, we wouldn't have been able to, actually prove why we can constrain the spin parameters to such high precision. And on top of this, if a near extreme black hole, if we were to detect a near extreme black hole, we need to ask a question of why, all right, it's spinning at such a crazy rate. How can it be spinning at such a crazy rate? This will break a limit called the Thorne limit, which is, one of the astrophysically, one of the maximum rotation parameters that you can have of these typical near extremal emeries, which is roughly 0.998. So if we were to detect a near extreme black hole, we know that Thorne's limit is simply not enough. There must be some more very exciting physics going on out there. So it's very important to look for these things, because if we don't look for them, we're simply not going to find them. So it's very important. Okay. So I'm going to give a quick crash course in data analysis, nice and straightforward. Yes.
Could you just comment? I mean, the Thorne limit comes from the thin disk model. Why is that interesting? It involves a lot of assumptions. It's analytical.
It does. No, I completely agree.
That has anything to do with anything.
Yeah, no. I completely agree. I think it's just the Thorne limit was something that a lot of people have accepted, but there are many other accretion models out there, right? So for example, super Eddington accretion can spin up black holes much faster than the Thorne limit can, right? Or, so I think that for the Thorne limit, it's not the end of the story at all. And there are a huge amount of assumptions that went into that. Okay, so I think it's important to, still be looking for these things. And in particular, I don't think that it's enough, but that's just my own view. Okay.
Can I ask a separate question?
Sure.
I may have missed this, but what signal to noise ratio for your data do you require in order to get those precise levels of spin estimation?
20. You need an SNR of 20.
SNR, okay. and that's within the specs of LISA?
Yes, it is. So the typical emery detection threshold is roughly an SNR of 20. Okay. So for typical astrophysical parameters that we plugged in, so we were looking at in spirals of, say, a 10 solar mass black hole going into a 10 to the 6 solar mass black hole at a distance of roughly a gigaparsec, we were getting SNRs in the range of around 80, okay, which is very bright.
Mm-hmm. Okay. All right, okay. Thanks.
No worries. Okay, so a quick crash course in data analysis. So a typical data stream will consist of some signal, that we're wanting to basically rip out of the noise. And that signal itself is characterized by a parameter set, which we're going to call theta. Now, this parameter set can consist of the masses and the spins and the distances and where it is in the sky. Now, for the purposes of this talk, we're not going to be considering parameter estimation. We're going to more be considering parameter precision. And a very useful tool to do this is a thing called the Fischer information matrix. Now, if you calculate a Fischer information matrix, you basically get for free how well you can measure certain parameters. And it's quite an intuitive sort of formula here. So this is just some ghastly inner product, which I'm just not going to include for the time being. But the Fischer information matrix basically encodes the amount of information in your waveform about a certain parameter. And then if you take the inverse and then take the square root and you look at the diagonal elements, that tells you how well you can measure a particular parameter theta. So a nice instructive example here is that if I was to perform very expensive Markov chain Monte Carlo algorithms, then I'd be able to estimate the parameter, but I get a level of uncertainty. Okay. What the Fischer matrix does is it allows me very quickly and very cheaply to estimate exactly what that level of precision should be. Now, when I plugged my near extreme waveforms into the cluster here, it took about a month and a half to get the results, whereas a Fischer matrix takes 5 minutes. Okay, so it's a very quick, easy, and cheap way to deal with this. Okay. So before I actually talk about the construction of the waveforms, I need to discuss the radial trajectory itself. So in this situation, because we're dealing with circular and equatorial orbits, we have an analytical expression for the geodesic energy. And this is given by this expression here, just by taking coordinate time derivatives. Now, the numerator is a dynamical quantity. It purely is determined by radiation reaction effects, and it encodes the rate of emission of gravitational waves traveling off towards infinity and down towards the horizon. Okay. Whereas the denominator in this situation is purely kinematical, is geodesic, is an analytical thing that we can work with. Now, the difficulty with this equation here is that the numerator itself is typically numerical. And to calculate this, we need to basically solve a thing called the Tukulski equation that gives you these metric perturbations off towards infinity. But details is a numerical quantity. And the way that we handled this was we used a prescription given by Finn and Thorne back in 2000. And the way that they parameterized it was they gave the leading order post-Newtonian term, and then they tacked on some general relativistic factor that basically encapsulates the relativistic dynamics of when you're very, very close to the black hole itself. Now, this is a numerical quantity. And in order to get this thing, we basically used an open source Tukulski package that was within this source called the Black Hole Perturbation Toolkit, which is unbelievably useful, by the way. But thankfully, due to the guys at Harvard, they were able to give us an analytical prescription for the energy flux when you're dealing with near extreme black holes and you're very near the horizon. So in this case, we've got the mass ratio here, eta. We've got some constants, okay? And then we also have the radial distance from the horizon itself. So the beauty of this analytical formula is that we're able to use this in our Fischer matrix estimates to understand why we get such high precision. So when we're dealing with year-long waveforms, so we're further away from the horizon, we use the numerical scheme. But when we're very, very close, we can understand our numerical results using the analytical result itself. Okay. So now that we have the radial trajectory, we can also look at how these trajectories would behave if we're dealing with, say, a moderately spinning black hole. So I was looking here at a 10 solar mass black hole falling into a 2 million solar mass black hole with a spin of roughly 0.9. And you can see that the radial coordinate typically monotonically decreases as a function of time, coordinate time, until the ISCO is reached. Okay, and it follows this sort of square root of t sort of behavior. Whereas in the case of the near extremal limit, it's very different. You get this monotonic decreasing, which is what you want, but you see the square root of t sort of behavior, but then you get this exponential decay as the ISCO is approached. Now, this would make sense because remember, we're dealing with Euler-Lindquist coordinates, and because we're near extremal and we're evolving up to the ISCO, it's very close to the horizon. So we're looking at an object that's getting very, very close to the horizon, and that's because of time dilation, we would essentially see it kind of plateau and freeze as it gets very, very close. And then if you were to work with the near horizon extremal pair spacetime, you can actually show this exponential decay using the formula for the flux that Gralla et al. Came up with in 2016. So you see that there are qualitatively different features between moderately spinning black holes and near extreme black holes. So now that we have the radial trajectory, we can build a waveform model. So in this case, we've got a small parameter space, which is the initial radius, the spin, the secondary mass, the primary mass, the initial phase, and the distance. And we use a semi-approximate waveform model, which is given by this horrible expression here. The important features to remember is that an emery is a superposition of many sinusoids, all of which are multiples of some angular frequency, which is defined as this expression here. And it depends on the energy flux heading off towards infinity. Now, this equation is very similar to the Tukulski prescription of the waveform itself, except from there are no spin-weighted spheroidal harmonics, and there are no Tukulski amplitudes. We've integrated out the spheroidal harmonics, and the Tukulski amplitudes are related to the energy flux. But there is an extra complex phase here, but we've just neglected it in this analysis. But this is purely just to help us with the analytical study of why we can constrain the spin parameters to such high precision. Okay. So using this waveform model, remember that the Fischer matrix governs precision on the parameters. We can plug this guy into the Fischer matrix, and in doing so, and making a few approximations, just due to ignoring subleading terms, you get this expression. Now, this expression is very powerful and actually quite beautiful, because what this shows is that, remember that the spin precision will scale as 1 over the square root of the inverse Fischer matrix. So we're trying to maximize this guy. So this guy depends on the energy flux heading out towards infinity. We also have roughly the number of cycles squared, but an important feature here is the spin dependence on the radial trajectory. Okay, so what was interesting about this is that when we derived this equation, we got a bit confused, because for near extreme Kerr black holes, this guy typically goes towards 0. This guy here, okay, is typically of order 1 over the mass ratio, so it's large, but and it is typically larger for near extreme black holes, but it did not explain the precision measurements that we were getting. So there must be something special going on with this character here. So the purpose of the rest of the talk is to try and understand how this guy behaves when you're working in the near horizon regime of these near extreme black holes. Are there any questions, by the way, before I proceed?
Yeah, I had a
Sure.
very small question here.
Sure.
So it's a well-known fact that the Boyd-Lingvis coordinate system is not well behaved in the limits of the horizon, right? And that is why a lot of MHD waveforms tend to use the Kerr coordinate system, for example. So what confidence do we have that there are no coordinate artifacts in the waveforms that we're modeling here?
What confidence do we have? I believe that our results, okay, right, let me think. Okay, so I believe that our results are not simply due to coordinate artifacts, because we were able to show that the spin precision would increase when you work within the near horizon extreme Kerr spacetime. So we did actually do a change of coordinates to make sure that the results we were seeing were not coordinate artifacts. Okay, and this is where I'm going to go.
That answer. Yeah, thank you.
No worries. Good question, by the way. Thank you. So in order to understand the spin dependence on the radial evolution, we can start off with the radial trajectory itself. And we were able to derive a first order linear differential equation that describes the spin dependence in the radial evolution. So doing some black magic and sorcery and witchcraft, we came up with this expression here. Now it looks quite horrible, but what we can do is we can try and identify the dominant contributions in this equation. So let's split them up. So first of all, we have a kinematical piece. This is determined purely by the geodesics of the problem. We have a radiation reaction piece, which I'm going to call the dynamical piece. And it turns out that for all spin parameters greater than 0.9, we were able to prove that it's the kinematical piece always dominates over the dynamical piece itself. Okay, and this gives us a lot more analytical control and a bit more of an analytical understanding about how the spin dependence in the radial evolution behaves, particularly in the near ISCO regime. So I've got some plots to kind of back this up. So just to remind you, we're trying to find an evolution equation for this guy because it's dominating, trying to figure out whether it dominates the Fischer matrix itself. And if you plot the kinematical pieces in comparison to dynamical pieces, you can see that they dominate, and it dominates by quite a lot. Remember that this is on the log scale, and I'm plotting against Boylan-Quist coordinate r, the dimensionless one. And this happens across all spins between these and a lot more spins greater than it. So because of this, in that solution to that differential equation for the spin dependence on the radial evolution, we're able to ignore the dynamical terms, okay, and only work with the kinematical ones as the source for the integrand. So we did this. We made some approximations and we found this expression here. So this is for moderately spinning black holes, and you see that you have this divergence as you approach the ISCO. Okay, and I've shown a plot here, so I'm just going to move myself. You can see there's a plot here. So we have the analytical approximation, and you can see that it matches the numerical approximation. So this is including spin dependence and including the radiation reaction terms in the evolution equation for the spin derivative and the radial trajectory. And you see that they match extremely well. And then also, and also when you work very near the horizon and you use the energy flux equations given to us by the Harvard group, we were able to show that the spin dependence on the radial trajectory follows this sort of behavior. So you see it diverges, it grows and grows and grows, not diverges, it grows when you get very close to the ISCO. And what we were able to show in the paper is that the spin dependence on the radial trajectory itself is typically much larger for near extreme black holes than moderately spinning ones. And this is a very important this is a very, very important point. And we believe that the actual constraints on the spin parameter are dominated because of this very large spin dependence on the radial trajectory. But we can go further. So in the paper, we computed the ratio of these Fischer matrices, okay? And what we did was we integrated all the way up to this point, which we're going to call the transition regime, which is just a point before the ISCO where you smoothly would transition from some adiabatic spiral into a plunging geodesic, okay? And it's defined at this sort of point here. And in doing this, we were able to come up with an expression. This is some horrible, messy function, but then you get this divergence, okay, as you get very close to the cutoff point. And what this shows is that the Fischer information matrix for near extremal black holes is much larger than moderately spinning black holes. And this leads us to believe that we require the system to be basically near extremal to get such high precision on how well we can measure the spin parameter. Okay, so this kind of concludes the analytical part. The rest are all just pretty plots. Are there any questions before I continue, or is this fine for the time being? Okay. Oh, yeah.
Just a quick question.
Sure.
What determines this R cut?
Ah, that's an excellent point. So what determines that R cut is typically when the quasi-circular approximation will begin to break down. And this is something that we studied in one of our papers on trying to model the complete trajectory from radial infinity down to the horizon. Okay, so we had the transition from adiabatic spiral to the plunging phase. And we were able to show that R cut, which is basically when you enter in this transition regime, scales according to the extremality parameter. But we also tacked on the scaling of when you would enter the transition regime for moderately spinning black holes, just to be that extra little bit safer. So in the analysis that I show you from here on, in the numerical results, we will cut the waveforms so that we do not get too close to the ISCO, such that the quasi-circular approximation could be playing an effect in our numerical results. Does that answer your question?
Yes.
Okay.
I can ask again at the end, I guess.
Sure. That's fine. Okay. So what we did was now we're going to deal with the actual numerics. We're not going to be dealing with too many approximations. So we used Tukulski-based waveforms. And in particular, we used a very large number of harmonics to get an accurate depiction of the signal. Okay, so for edge-on sources, you require a huge amount of harmonics to get an accurate representation. So we used the first 20 harmonics here. Okay, and we believe that this was a suitable approximation because as we increase the number of harmonics, we lead to overlaps between the waveforms. We found that there was very, very little difference once you went from LS20 to 21, etc. But the important thing is that for near extreme black holes, you require a huge amount of harmonics to properly represent the frequency evolution and the amplitude evolution itself. And these signals have a very complicated harmonic structure, right? So we use the black hole perturbation toolkit in order to basically build interpolants for the spin-weighted spheroidal harmonics and the Tukulski amplitudes themselves. So here are the plots that I showed you before for both face-on and edge-on sources. Okay, so like I said before, you get this nice profile, and then you get this exponential sort of dampening towards the end. Now for the face-on signal, you just get the one harmonic, whereas for edge-on, it's a lot more complicated. You get lots of harmonics there, okay, and you need to take them into account. Now, the question we now want to ask is, okay, so if we did see a signal, how much signal to noise ratio, okay, which is a metric to determine how bright your signal is built up in this in-spiral regime and in this dampening regime, okay? So we did this, so we did some calculations, and under various typical astrophysical parameters, so like I said, a gigaparsec for a 10 solar mass falling into a 10 to the 6 solar mass black hole was giving us SNRs of roughly around 80.
Okay,
so
Siri,
we
set timer for 20 minutes.
Oh, is everything okay?
22 minutes.
Okay.
22 minutes, starting now.
Andy, you need to mute yourself.
It's fine, it's fine. Okay, so we're looking for SNRs of 20. Okay, so in the in-spiral regime, for the light source that I showed you before, so that's 10 solar mass falling into a 10 to the 6 solar mass black hole, the in-spiral regime typically gives you about 96% of the total SNR, whereas the dampening regime isn't actually that loud. Okay, for the face-on source, it's a little bit louder, but not so much. But the reason for this is simply just due to the actual frequencies of the signal. Okay, so near extreme black holes typically offer gravitational waves that are quite high frequency because the particles spinning around so quickly, essentially. And because we're considering so many harmonics, around 20, a lot of those frequencies are smeared out across the Lisa sensitivity curve. So it's for this reason as to why the dampening feature doesn't contribute that much to the SNR, but this isn't too much of a problem, because what this says is that assuming that the in-spiral regime is resolved, then we will be able to actually dig the dampening feature out of the data stream itself. Okay, so now that this is all over and done with, I can present some of the results that we found. So in this situation, if you look at the plots on the bottom left, for spins of roughly 0.9, you're constraining the spin parameter to roughly a few times 10 to the negative 6. This is great. But when you're dealing with near extreme black holes, you're able to constrain the spin parameter 3 or 4 orders of magnitude more great, right? Now, in this situation, I was considering in spirals of, say, a 10 solar mass black hole falling into a 10 to the 6 solar mass black hole, or a 10 solar mass black hole falling into a 10 to the 7 solar mass black hole. But you can see that in the case of when they're near extreme, you get very tight constraints. And the rest of the parameters are fairly weakly affected. This is what you would see for just kind of standard moderately spinning black holes. It's the spin parameter precision that is very, very, very affected. Okay. Now I have exact and approx here. What I was doing in this situation was, in the exact case, I was including spin dependence on all of the radiation reaction terms and the spin weighted spheroidal harmonics, in order so that I could compute actual proper numerical derivatives of these things. Whereas in the approximate case, I was relaxing the assumption of spin dependence on the Tukulski amplitudes and the spin weighted spheroidal harmonics themselves. And what we could show was that the approximate Fischer matrix estimates match the exact one very, very well. And the reason for this is because, remember, as I said before, it's the kinematics of the problem that really drive the spin precision rather than the radiation reaction pieces. It's that growth in the spin derivative of the radial trajectory in the dampening regime that is driving this precision, okay? And the pieces that are encoded in that, the radiation reaction pieces and the geodesic pieces, it's the geodesic pieces that dominate that, okay? So then we looked at the in-spiral and then the dampening feature. And what we were able to conclude, if you look at the bottom left again, is that the dampening feature is absolutely necessary in order to make such tight constraints on the spin parameter itself, right? And if you were only to measure up to the dampening feature, you would be able to recover the parameter to 1 part in 10 to the 7. So the take-home message is the following. You need to observe the dampening feature in order to make such tight constraints on the spin parameter itself. And then finally, we took the spin parameter towards unity, and you can see that the spin parameter precision increases exponentially. Okay, so the more near extreme your black hole is, the better you'll be able to recover the spin parameter itself. Okay, so
can I ask a question here?
Yeah, of course you can. Go for it.
Yes. So like delta A divided by A is very small, but
it's a relative precision. Yes.
What would it look like for delta A over 1 minus A?
Over 1 minus A.
Yeah.
It would look like. That's an excellent question. I've never thought about this. Well, it would. I don't want to. I would say it would be strictly less than order 1, but I'm not too sure. Actually, I would need to think about this. To be honest, I don't want to, say anything mistaken to you. I'm not sure. I think that I'm just curious. So that's a good point. What made you think this?
Yeah, because
I mean, I'm comparing like relative precisions here. That's the thing I was focusing on. What would 1 minus A tell you? This is a genuine question. I'm not sure.
It's kind of arbitrary to use a certain parameter, and then for this context, the natural parameter seems to be 1 minus A. Is it's like the most special when that parameter goes to 0 rather than when A goes to 0.
Oh,
I think the
see.
length of the throat is log 1 minus A, isn't it? So it's kind of what you're saying, that it's what you can measure as the length of the throat. And of course, if you measure the length of the throat to some accuracy, you know the spin to some incredible accuracy.
Yeah, indeed. And that is definitely the case in this situation. Yeah, so the throat is determined by the log of 1 minus A from what I can remember. And I guess being able to measure the length of that throat would be the thing that would govern how well you can measure this parameter itself. So no, that's a good question. I never thought to phrase it like this, to be honest. Thanks for your input. Yeah, that was interesting. Thank you. Okay, so I'm nearly done, and then we can discuss some of this stuff a bit more in detail. So I presented you these Fischer matrices, but there may be people in the audience that would be a little bit worried, because the Fischer matrix itself can typically be quite unstable. Okay, it's a very hard calculation to do, typically because these Fischer matrices have very high condition numbers, meaning that calculating the inverse is a very tricky thing to do unless you have very high precisions. Okay, so what we can use is we can use an independent procedure to basically verify our Fischer matrix results, right? And this is Markov chain Monte Carlo. So quick primer here. This is Bayes' theorem. You'll all have seen this, but this here is the posterior distribution representing our distribution of beliefs on the parameters theta given the data stream, and is made up of a product of the likelihood function and the prior distribution, which represents our a priori beliefs on the parameters themselves. So what we did was we basically injected a signal into some noise to make it a little bit more realistic and try to recover the various parameters of the source. And the results were amazing. Okay, I was almost in tears when I saw this, actually. I was so happy to see this. And what we found was that the precision at which we can measure the spin parameter itself, okay, is properly reflected by our Fischer matrix results. And this implies that the results that I've shown you today are not subject to very difficult numerical instabilities, and that they properly show how well we can constrain this parameter, which is really quite exciting. I've got the other posterior distributions in a backup slide later if other people want to see, but the story here is that the Fischer matrix is a very, very accurate prediction. Okay, so the point here, and the thing that you guys should take home, is that if you have observed gravitational waves coming from a binary where the central black hole is near extremal, then you should expect immensely tight constraints on the spin parameter itself. Okay, and that's hopefully what you guys can leave with thinking today, is that if near extreme black holes were out there, LISA certainly, in my opinion, is one of the best bets in finding them. And in particular, we'll be able to constrain that spin parameter to unprecedented levels of precision. Okay, so a couple natural extensions. This is one that I'm excited to do. And this is basically to incorporate the transition from spiral to plunge into our waveform models and try and figure out if incorporating that extra level of physics into the problem enhances our ability to measure the spin parameter. Okay, this will be a very interesting project. If anybody is interested, let me know. But this is something I'm really excited to work on. And on top of this, there are some further extensions, this is something that we're working on right now, which is extending our analytical results for the spin, but looking at all of the other parameters themselves. So for typical Emery observations, it has been noted in the past, but only numerically, that the precision in which you can measure the parameters gets much better the closer to the ISCO you are. So we're trying to basically verify these results using some analytical study, okay, particularly in the near extremal regime. We're also going to try and extend this parameter space to try and include things like eccentricity or inclination in our waveform models and orbits. Okay, now this is very, very exciting. And the reason it's exciting is because if you have a Emery where the primary is near extremal, but it's eccentric, then you're going to have a zoom and a whirl phase. So you have the whirl phase where you're orbiting around, and then you have a zoom where you zoom away, and then you whirl, and then you zoom away. Well, the whirling phase, when you're zooming around, the actual gravitational radiation amplitude is suppressed. But then in the zooming phase, the amplitude of the gravitational waves is then enhanced. And this is very different from moderately spinning black holes, okay, where it's the total opposite, right? So by the introduction of this extra physics into the problem, we're curious whether the spin parameter, if we can measure it as well, or maybe there's extra degeneracies that will, end up cropping up. We don't know, but this is something that we're looking at with Joanne Simon at the moment. And finally, and this is more in line with the stuff that I get up to, is dealing with a proper systematic study of the waveforms that we're considering. Okay, and what I mean by this is, how accurate do our waveform models have to be able to successfully strip that signal out of the data stream itself? Okay, so because the spin parameter can be measured with such precision, it requires very, very accurate waveforms to pull that out, so that the biases that we would recover on the parameters are typically much smaller than the width of the actual posterior itself. So it needs to be well contained. In that situation, you would say the waveform model is accurate enough so that it can successfully pull the signal out with insignificant biases on the parameters. Okay, so that's me finished. And I just want to say that in preparation of doing this, I remember the first time I generated one of those edge-on near extremal waveforms, and I showed it to one of my friends, and he took it and basically butchered it. And this is Pumbaa right here. And I think it works beautifully well. So whenever I incorporate these near extremal waveforms in our data analysis toolkits, which I plan to do, hopefully, it will be very much from Pumbaa import near extremal waveform. But thank you so much for listening. I really appreciated talking to you today about the stuff that I've been up to. And I'm more than happy to take any questions or discuss anything that I said before. But thanks, that was good fun.
Thank you. Thanks, Ollie. That was great. So yeah, we have time for questions. So you can either raise your hand or unmute yourself and ask questions. So we have a raised hand from Aditya.
Yeah, hi. So that was an amazing tour de force of Lisa's capabilities and an excellent talk. So the question I have is a technical computation question regarding the spin-weighted spheroidal harmonics.
Oh,
because,
okay. Here we go. Sure.
To the best of my knowledge, the black hole perturbation theory toolkit expands those functions using a real frequency parameter expansion. Now, that essentially is not physical because quasi-normal modes govern complex frequencies, and you require spheroidal harmonics to be useful for complex parameters as well, which arise from, as you well know, from the radial equation, the Tukulski radial equation. So how exactly was the spheroidal harmonics useful in this case, and isn't using them for a real parameter kind of getting away from the physics of the problem?
I don't think so. So for the spin weighted spheroidal harmonics, I mean, what we did was we used, hang on a second. This is the Tukulski prescription that we used in the end of the day, right? So for face on, we had this function G here is given by this horrible expression here, which is given by the spin weighted spheroidal harmonics, right? With the Tukulski amplitudes themselves, okay? And the ones that we used in the actual spin weighted spheroidal harmonics package, I think that was meant to numerically solve the angular part of Tukulski's equation, from what I remember. And we didn't see any artifacts or any problems as we were working with it, I don't think. And also another thing as well was that in the results that we have, when we included spin dependence, as in the A dependence, on this contribution itself, it didn't actually affect the results that much. So even if there was such a problem, I highly doubt that they would be causing, that they would be influencing our results. I don't think. Okay.
Actually, I have a follow-up question. I'll continue on chat, seeing there are quite a few other questions. Thanks so much.
Yeah, go for it. Go for it. No, it's good. Go for it. What's your question? If you're speaking, I can't hear you.
No, I could continue it on chat. I see a lot of other questions as well. So
okay,
no
okay, fine.
Yeah,
and I'm more than happy to talk about this stuff offline as well. If you just want to drop me an email, and we can chat about it. I've no problem with it.
Alex is next.
Yeah, I just wanted to make a cute point. I liked you showing the image of Gargantua at the beginning of your talk.
Thank you.
And actually, that image is noticeably not showing a high spin black hole.
No, yeah.
and I put in the
You're
chat,
right.
so they actually simulated a near extreme black hole, and that has a very sharp, bright line, which is sometimes called the neckline. And they thought it was too weird for the movie. So even though they call Gargantua, I mean, it is, for the purpose of the story, a very high spin black hole. The actual simulated image shows a black hole of spin 60% because it's less crazy.
No, yeah, you're right. Did they not also as well? So apparently the black hole in the film, if they did do it properly, it would have been so massive that it just would have completely encapsulates the sky. And I think Christopher Nolan basically looked at this and said, we can't have something like that. So they basically ended up changing things. But no, yeah, awesome point. Thanks for that addition. That was cool.
Yeah, Shep.
Yeah, let me just add that that wasn't the only thing not quite right in Interstellar. There were some other things as well, Alex. So good that you pointed that out. I was actually thinking that as I was watching it, though, too. That so like I think that photon orbit does not look asymmetric enough. But we could talk about bookcases and black holes and all that stuff. But let's not even go there. The question I had was, and again, forgive me if I've missed this, but the precision of determining the spin, aren't there some degeneracies associated with that, up to and including orientation of the relative spins of the merger?
We in our analysis, I don't think that we saw any such degeneracies. Okay, when we're looking at face on, I mean, we only looked at two different viewing angles. We looked at face on and edge on, and edge on was the more sort of extreme limit, right? Because that's where the waveform model gets the most complicated, because you require a huge number of harmonics. But one thing that we did not do is we did not include theta and phi as actual parameters in our waveform. Okay, that is an assumption that we made. We didn't think that they would be, we didn't believe that they would be particularly degenerate, and this is one of the reasons as to why we did not include them. But this is something that we're going to be looking at later on, is to basically we're planning to extend the parameter space, right? That the goal here is to look at a fully generic orbit and try and figure out how well we can constrain the parameters when we include eccentricities, inclinations, the theta and phi, where it is in the sky, that is the end gold standard of where we want to be in the next couple of years, right? So that is something that we're going to be looking at as a follow-on study to figure out whether the spin could potentially be degenerate with these angles here. Okay.
Okay. Yeah, they're very interesting to see if that's true. Thank you.
Yeah, no, absolutely, absolutely. Good question. Thank you.
So Harry, you're next.
Hi.
Hello.
So I wanted to ask, thanks for the nice talk. I wanted to ask, so these extreme accuracies with which you can measure the spin raise the following question for me. So you basically assume that you're deep in the extreme mass ratio regime, right? You're neglecting all effects of back reaction. You're working only to first order in the mass ratio.
We're only first order in the mass ratio, indeed. We haven't looked at any
But
other higher order
presumably
effects.
when you're close to such very high spins, you may actually, so if you have an extreme a mass ratio of 1,000,000, you can actually maybe see effects on the spin of the black hole during the merge, right? You can see a difference between the initial and final spins. Did you think about that?
Yeah,
kind of thing?
so let me just make sure I'm on the right lines with your question. Is what you're asking is about the kind of the dynamic variability in the spin parameter throughout the inspiral regime.
Because of basically because of back reaction. I mean, if you have 10 nines and you're throwing in something with mass ratio 1,000,000, you would expect a change in the spin parameter, or maybe at least that it's plausible.
This is something that we did not. This is something that we did not include in our models. Okay, and this is something that we are going to try and include in our models, because I think it was the Inspiral into Gargantua paper, they had a discussion about this, right, where eventually, due to what was it, the gravitational waves basically being absorbed, the spin parameter itself will typically decrease, from what I can remember. But we didn't include this in the analysis.
Generically, I would believe it would decrease. Yeah.
Yeah. We didn't include this in the analysis. We weren't, being honest with you, I'm not particularly sure how we would include this in the analysis until we had more accurate self-force information, higher order self-force information. But I'm not sure. I'm not sure. This is something I'll need to think about. That's a brilliant question.
But I think it's a very interesting point. I mean, maybe a way to use your very accurate way to do this. That would be super interesting.
No, this is really cool. This is giving loads of extensions to this work. This is excellent. No, good question. Thank you.
All right. Are there any other questions? Perhaps I can ask one question myself. So one of the messages that you conveyed is that this extreme precision is a result of the radiation reaction terms being less important.
Mm-hmm.
Of course, they're still important in the sense that they provide you the inspiral. Otherwise, you just have a single.
Yeah, that's true.
But the radiation reaction terms are also what are responsible for the transition to Planck, from inspiral to Planck. And I think there were papers which discussed the fact that in this near extreme regime, that transition is also becoming special. And can you comment on how special it is, whether the radiation reaction terms make the transition smoother, and whether, how difficult will it be to not have to decide our cut, but have a waveform that will go through this. And do you expect that this is an important thing in terms of the precisions that you're discussing?
So, okay, let me try and collect my answer as best I possibly can so it's somewhat coherent. Right. So yeah, so the transition regime is very special for near extreme black holes, okay? And the reason being is because the typical transition right, which is the transition from some adiabatic and spiral into some geodesic plunge, can be solved using the Ori-Thorne procedure, right, which is where you typically Taylor expand the geodesic equations around the ISCO, and then you assume some relationship between E dot and L dot, and you're able to come up with a transition equation of motion that glues the adiabatic and spiral into some geodesic plunge. Now, for near extreme black holes, it becomes a lot more complicated because of the existence of this long throat, and you end up constructing 3 different transition equations of motion that are purely determined by the relationship between the mass ratio and the small, the extremality parameter defined by the square root of 1 minus a squared. So depending on how they both, how comparable both of those are, determines what transition equation of motion that you can use, okay? So in terms of the actual self force itself, I think we were able to, we were able to prove that the conservative piece of the radial self force is negligible throughout that regime. However, the dissipative piece is very important. And that dissipative piece itself, from what I can remember, when Ori and Thorne did this in the past, they assumed essentially a constant relationship. So they basically had that E minus E ISCO was given by some omega L dot, tau minus tau ISCO. Whereas you need to include, I think, these, you can't approximate the flux as being a constant throughout the transition regime, which is what a lot of people did in the past. For a near extreme curve, you need to basically encode these deviations from the linear and proper time evolution of the energy flux itself. So there are some special features that happen in this transition from a spiral to plunge, unique to near extreme black holes than for moderately spinning ones. Okay, so in terms of this is what I think is the most, what will be really interesting about this project is that what I said to you before was that the spin dependence on the radial trajectory is what dominates the spin precision. And the part that dominates that are the geodesic parts, not the radiation reaction pieces. But you need those radiation reaction pieces in the transition from a spiral to plunge, right? So what we think will probably, trying to understand this analytically will be challenging, okay? But numerically, it would be, I don't want to say it's straightforward because nothing's straightforward, but I think numerically, that is something that we have a grasp of, and we believe that you would expect tighter constraints if you were to incorporate the transition from spiral to plunge, okay? Sorry for that totally long-winded answer. It was a very good question. Is there any other follow-up questions that you have on that?
No, that was good, thanks.
No worries.
So if there are no more questions, and I don't see any raised hands, then we should thank Ollie again for a very nice talk and the stimulating discussion. And we'll see everybody next week.
Thank you guys very much for hosting me. That was amazing. Have a wonderful day.
Okay,
See you
thank you.
later.
Bye-bye.
No worries. Bye.